Good morning, everyone. So I'm going to start just to give this brief introduction, and maybe we can also leave some minutes for other people to join. Um, so this is the third webinar in our Hydra series. We have been organizing some webinars regarding our technical activities, and this is now the turn of our more experimental activities regarding the development and test of a new monitoring tool for hydrogen leakages. And we also take the opportunity for this webinar to involve other speakers from other projects and increase the knowledge that we can give to the audience who usually attend our webinars, and also increase our networking. So we have here Nelson Rafael Perozo from Technical University of Clausthal, and he will give a presentation about his activity in the CER project. And then we have Ceres Woolley from the University of Utrecht, and she will talk about her research activities on how to distinguish between green and blue hydrogen with isotopic measurements. I think that we can maybe already start with the first presentation. So the first one is going to be the presentation of the Hydra solution, so the instrument itself. I will leave the floor to Veronica Cronagliati from Automa Company. So the floor is yours. You can share your presentation.
Can you see it?
Yes.
Okay, good. Thank you, Rossella. Good morning, everyone. I'm Veronica Crognaletti from Autona, and the title of my presentation is Hydra Solution for Hydrogen Leakage Monitoring. So, can we start? Okay. Only some words about my background. I have a master's degree in biomedical engineering, and I joined Automa in 2020 in the process control division. One of the main activities of our division is to follow the full life cycle of the research and development projects. So from the proposal writing, consortium building, to the project management and reporting, and then to the post-funding monitoring. So also in Hydra project, this is my role. Automa was founded in 1987, and now he's in more than 40 countries along the world. He's a company that design, engineers, and manufacture made in Italy technologies, so electronic device for remote monitoring in oil, gas, and water sector, both for the cathodic protection and operating parameters along the distribution and transportation networks, so in the pipeline. Also in Hydra project, our role is to develop the advanced sensor for hydrogen leakages, so for the detection of hydrogen leak, and also its remote control system. Before looking at the sensor itself that we developed, it's important to answer this question. So why hydrogen is hard to detect? First of all, it is invisible to IR sensor. Infrared absorption sensor are not able to see hydrogen. Second, the hydrogen is the smallest molecule of all, so we need a rapid and reliable detection. In addition, the third point is that hydrogen is flammable also with low ignition energy. And fourth, in the field, so in nature, hydrogen is not pure. So we need a selective multi-gas detection for our sensor. So our answer is the Raman spectroscopy. Hydra monitoring tool is built on Raman spectroscopy that is based on this assumption. Light scattered by gas molecules carries a unique spectral fingerprint for each molecule, for each type of molecule. So this type of spectroscopy, Raman spectroscopy is able to detect and identify whole molecule simultaneously. So it is also high selective, but more important, it is quick and non-destructive type of measurement with no sample preparation. So we can do this type of measure also in free air. The Hydra monitoring system. It is a single integrated instrument. Both the hardware and software part are developed in-house by Automa, and the monitoring system is organized in 3 functional blocks. The first block is the sampling unit. So it is composed by a tubing system and an ATEX classified pump. This part is designed in order to ensure uniform sample collection from the field and so from the key leak points. The second part is the optical unit, so the Raman core of our sensor, and it is based on a laser source, the probe, the focusing optics, so both lens and windows, the measuring cell, and the spectrometer, of course. All of these parts are housed in an ATEX certified box, able to work also in hazardous areas. The third part is the data processing part, the data processing unit. It is based on a software developed by Automa that is web pressure. Thanks to this, we can allow the acquisition, the analysis, and the storage of sensors data. In addition, this part is connected to an alert mechanism that is triggered above the 1% of hydrogen threshold. This is an image of our monitoring system. As you can see, inside the box, we have the laser source, the Raman spectrometer, the probe and the focusing optics. So as I said, with both optical window and lenses, the measuring cell, and also the ATEX EXD box. You cannot see the software, but as I can said, that is web pressure developed by Automa. Since the Hydra project is a research and development project, we have had some key performance indicators. For example, we have a detection range from 0.1 and 100%, an accuracy higher than the 0.1%, and a response time lower than 1 minute. In addition, we also have to respect some safety and regulatory constraints to design our sensor. So we need a NATEX Zone 1 certification in order to work in hazardous conditions. We have a requirement defined through site inspection and also with an ASOP study. As I said, also an alarm that is triggered above the 1% of hydrogen threshold, and we need to comply with the gas detection safety standards. During the first campaign of test, we noted a spectral background in the area of the hydrogen region when we can have the peak of hydrogen. But thanks to our work, we can say that this type of background is an instrumental noise, not a real signal, because it is independent of release pressure, visible even in free air acquisition, and in addition is stable in its spectral position. So we can say that the interference was material dependent. For this reason, we have tried to correct this type of artifact, not so only in a software way, but also in a physical hardware way. We have selected different type of optical materials, both of lenses and window, and we select the best one, so the calcium fluoride Raman grade optics, lenses and windows, thanks to its clean baseline in the hydrogen region. So the background in the hydrogen region was eliminated thanks to this type of optics in a hardware level. But in addition, we also add a software update because the previous compensation algorithm that we have introduced have been recalibrated for clean baseline. So now we doesn't need hydrogen-free reference measurement, and we are able to do this type of measure also in a free air, where we cannot know if hydrogen there is or not. And also we have a reduction of the measurement time. A second challenge is revealed by other field tests because, as I said before, hydrogen is lighter than air, so the leak plume rises and its peak is drift by several millimeters. So now the current configuration of the probe is a single probe of 8 millimeters, but we are designing now a new solution, so an hexagonal probe with 7 inlets. This proposed solution is able to spread the sample over these 7 inlets, so we have not dead angles. We have a distributed capture and a stable pre-inlet flow. The last two things, we have a safety milestone that is most important because each individual sensor is tested and certified safe for use in potentially explosive hydrogen atmosphere, as I said, and this is the image of our certificate. And in addition, some next development for the AI. In fact, we have developing a predictive module in order to anticipate risks and critical situation from the field. Now we are in the phase of training our sensors, so this type of module, because we need a large and high quality data sets. And also we are facing with the EU AI Act in order to guarantee safety, transparency, cybersecurity, and compliance. These are another time my contacts, and thank you for your attention.
Thank you, Veronica. We will take all the questions at the end of the webinar. So if any of the speaker has any question, please drop them in the chat, and then we can go through them after all the presentations. Now we have the presentation from Raffaella Gerboni from Politecnico di Torino. Her presentation is connected to the one Veronica just gave because actually Raffaella was involved in the activities of testing the sensor. So we will hear about this in her presentation. Raffaella, the floor is yours.
Many thanks, Rossella. So good morning to all of you, also from my side. My presentation will be about the testing of hydrogen leakages in a confined environment, and especially on the deployment of this wind tunnel that was used during the Hydra project. Okay, well, about me, I am a nuclear engineer and I have a PhD in energy engineering, and currently I am the CDOG DENERG laboratory coordinator under the scientific responsibility of Professor Carpignano. And I have been working throughout my academic career on hydrogen, life cycle assessments, and security and safety, both of them. So at present, I am a member of the technical staff, and as that, I support the utilization of the wind tunnel that I'm presenting shortly. So here is the agenda of my presentation today. I will introduce you the CDOG and the CSTA framework, and then I will give us some kind of details about the methane and hydrogen testing safety issues that we encountered in our laboratory. And then I will give you also some details about the upgrades that we made to our wind tunnel in order to be able to do pure hydrogen test releases. And then I will show a summary of the Hydra test results, focusing on the different configuration that we were asked to consider. And finally, the next steps that we are going to carry out. This is the short story of our lab. We all started in 2015 when the CDOC laboratory was funded with the economical support of the Italian Ministry of Economic Development. That was the title of the name of the ministry at that time. CDOC stands for safety, it's an acronym that stands for Safety and Environmental Analysis Division for Oil and Gas. And in fact, it was born for focusing especially on oil and gas issues. And the first important output of the lab in 2017 was a paperwork. It was a guideline for the report on major hazards that each company has to compile for each oil and gas offshore production platform. So it's mainly related to safety issues. So this outcome was particularly appreciated by the ministry, so that we received further support. And in 2018, there was the birth of the CSTA Competence Center at Environment Park, which is a technological park here in Torino. So the facility is not in Politecnico, it's outside Politecnico in this park. In 2020, the Italian Institute of Technology joined the group, so Politecnico and Environment Park, and joined the CSTA Competence Center. One of the key features of the Competence Center is the wind tunnel. So you see a description of the facility. It is a subsonic open flow wind tunnel. So the air comes from outside through the contraction section, crosses the test room, and it is aspired by the fans. It is ejected on the back through an air shaft. The maximum speed that we can reach at the moment in this tunnel is 8 meters per second. And the key feature is that the test room is quite large. As you see, it's 6 meters wide, 5 meters long, and 2 meters high. And we have the availability of up to 100 kilowatts of power. Part of that, of course, is used for the fans. And we have a gas supply. In fact, we have two gas supply lines. I'll show you briefly. There is a possibility of completely remote controlling the testing, because here above we do have a control room, an elevated control room with a large window from which we can see what's happening downstairs. The first use of this wind tunnel was dedicated to the testing with a mock-up of an offshore gas production platform, the one that you see here below. It is a 1/10 mock-up of a real platform of the kind that you can find in the Adriatic Sea. And we released onto this platform a gas mixture made of methane and air. The purpose of this testing was to validate a CFD tool that we were developing in our CDOG lab. You may know that modeling with the CFD high pressure releases is quite tricky. So we identified a different way of modeling, and we needed some kind of validation, experimental validation. Everything was scaled, of course, in this testing. So the platform was scaled, but also the pressure release and the wind velocity was released. So, okay, we can go up to 8 meters per second in reality, but in case you have a testing facility that is scaled down, also the wind has to be scaled down. So in practical, you can realize a wind that is representative of more intense wind. Here is the series of equipment to say that we have in the wind tunnel. So we started from a storage of gas. So we had a big storage facility for cylinders of up to 150 bars. Then this gas at that pressure was passing through a pressure reduction section in order to be able to reach the release point with this nozzle at a pressure of up to 10 bars. And then the gas, the mixture, was released onto the platform, onto the deck, where we had a series of obstacles sensed. So the black dots that you can see here are the sensors for detecting the concentration of the cloud, in fact, of the methane cloud. But then after this first phase, where we had this mixture made of 2.2% of CH4, so a half of the lead, so we were exploiting a fully non-flammable mixture, we decided to switch and to upgrade, because these offshore platforms today are in quite a large number, at least in Italy, going towards decommissioning. So there are a variety of studies to investigate the possible reuse of platforms, for example, for the re-injection into the depleted reservoir of CO2 or of hydrogen or hydrogen blends. So again, safety issues may arise from these activities. So we decided to investigate these kind of safety issues, releasing pure hydrogen or pure CO2 onto our mockup and see what if. So this is the new version, the one that we have also used in the Hydra project of the mockup. You see that we changed the paint because this paint is fully conductive in order not to give birth to any kind of spark or injection because hydrogen has a very low energy of activation. So the mockup itself is grounded, and all the sensors have the electronics that are insulated. So here you see the resin. And everything has been checked and certified by TÜV for being suitable for working in ATEX Zone 1. In fact, one of the activities that we have carried out in order to be able to use pure hydrogen into the wind tunnel was an ATEX study. The main part of the test room is ATEX Zone 1. Just to remember, Zone 1 is an area where explosive atmosphere is likely to occur occasionally. In fact, we are sure that will be an explosive atmosphere, but it only happens sometimes, so occasionally, when we do the test. So this is compliant with the definition of ATEX Zone 1. We made a series of simulations, both with fast and ANSYS fluent, in order to identify the extension of the zones, whatever the direction of the release. So this, you see, this is the final one, the big area where we must consider equipment that are suitable for working in Zone 1. There is a small Zone 2 here that is just at the entry point. There's a flange here at the entry point of the gas supply line. This is the previous gas supply line, the one that was carrying the mixture, the non-flammable mixture. That was why I was saying we have two gas lines, in fact, into our wind tunnel. With the ATEX study, we also identified limits for our experiments. We can carry out releases with the maximum hole size in the nozzle of 3 millimeters at a maximum pressure of 10.6 bars. The minimum wind speed into the tunnel must be 1 meters per second, but we also have a minimum release pressure that is 5 bars, because if the pressure is not enough, we run the risk of having the gas that has a low inertia and tends to go upwards towards the ceiling when where gas pockets can create, so creating dangerous situations. Before the testing with Automa sensor, we carried out some simulations of the possible releases because we have a constraint to carry out tests with the sensors put into a position where not more than 10% of concentration hydrogen was present. This was just a safety issue related to the fact that it was a prototype, so we didn't want to run any kind of risk. So we studied with our own new model, the SPAM model, the release of the gas. Just a brief explanation of what is this model. We split in two parts the release of the gas. The first part, that is the supersonic release, in the very vicinity of the release, we can consider a small dominion where we have a supersonic speed, under expanded jet, and the gas can be considered compressible. Far away from this initial volume, we do have the dispersion phase where we can consider the gas as incompressible and the speeds are subsonic. So you see that here we have this box, red box, that is this one, that is calculated and simulated before. So we do a coupling of the two simulations. We take the values of concentration and speed of the outer part of this box, and we put it here as a supply to the new investigation. So with this model, we are able to create maps that forecast the possible distribution of concentration. So the release that you see here is our nozzle, our source box, that is depicted in reality. And as this model was developed for the first time for oil and gas platform, where we have a very congested environment, we also put this obstacle in front of the nozzle to represent the congestion of a real platform. So this created further turbulence in the release. So we used this tool to make a forecast of the possible safe position where to put our sensor, safe meaning around 10% or not more than 10% of concentration. So here, for example, you see urban setup configuration. We have the nozzle put in the middle, and we have the distribution of the concentration. So based on this map, we decided to position also for the tunnel setup configuration. Urban setup and tunnel setup, because from the Hydra project, we had a series of configuration requested. The first one was the urban setup. So it was meant to test the sensor functionality in congested environment. So in view of possible deployment of hydrogen in domestic application, for example. So we realized this setup using our mockup as it was in the past, the sensor in the middle of the deck, and the source box had this obstacle just in front to increase the turbulence. The same, the following setup, the following configuration was a tunnel setup in order to test the functionality of the sensor inside a confined environment in view of the deployment of hydrogen in mobility application, for example. So we used our mockup without some obstacles in order to be able to host a mockup of a tunnel, road to tunnel. The sensor was put inside of the mockup without any obstacle in front of the nozzle. The same configuration was also used for testing another request, that was the hydrogen methane mixture. So we released this mixture inside of the tunnel, put the sensor there, and the purpose was to test the functionality of the sensor with different gases in view of a possible utilization of hydrogen blends. For example, inside of pipelines where we cannot carry pure hydrogen immediately, but we may prefer at the beginning this mixture with methane. And last configuration is the high atmosphere configuration. We wanted to test the functionality of the sensor in open air in view of industrial application when we have releases from stacks or in open air or from airplanes, for example, in case it is used liquid hydrogen for fueling airplanes. We used our mockup without many obstacles in order to clean the volume, to remove congestion, and the sensor was anchored to the ceiling, so in a upper position with respect to the previous ones. Accessories, I mentioned this mock-up of tunnel. In fact, it is a mock-up of the Fréjus tunnel that is between Italy and France. It is 1 meter long and 30 centimeters wide. You see our nozzle that is spraying inside of the tunnel. And also this mock-up, of course, was conductive. And for the Hydra testing, we consumed almost 6 bundles of 16 cylinders of gas at 200 bars, so a lot of gas. We also used the 4 cylinders of a mixture of hydrogen and methane mixture. It was a mixture made of 10% of hydrogen in methane. So the first setup was the urban setup, sensor put in the middle, spray with the obstacle in front. The second kind of setup was the tunnel setup. You see the tunnel put onto the deck without other obstacles. And you see that we inserted the sensor in 4 different positions. This is the corner position. We also put in the middle of the tunnel. We inserted it up to midpoint, so 50 centimeters inside of the tunnel, but also just very near to the exit of the tunnel, because the plume of the release had a certain forecastable shape. So we wanted to put the sensor in different position. And inside of the tunnel, so from this nozzle, we released pure hydrogen and the mixture in 2 different situations. And the last one is the high atmosphere configuration. So you see, we removed many obstacles, and the sensor is just hanged on the ceiling of the deck. As Veronica said, we had 2 campaigns. So the first one was with initial lenses, the initial materials. We did have some kind of results that led Automa to investigate new solutions, because we had a quite good relationship between the wind speed and the concentration measured by the sensor, but not so sensible reaction of the sensor to the pressure. So both in the urban and in the tunnel setups, the situation was some kind of questionable. So the Automa changed the lenses, as Veronica explained, and we had a second part of the campaign where the results were more meaningful. In fact, we had less spread of the results. There was a pretty good coherence between the pressure release and the concentration measured by the sensor. We noticed some kind of sensibility to temperature. You see releases at low temperature with quite a fixed value and a higher value in pressure, while at normal temperature, quite a higher temperature, we had a lower measurement, which was the representation, in fact, of the reaction of the gas to the temperature. And we also notice a sensibility to the turbulence. So that's why Veronica was mentioning the new idea of the redesigning the head of the sensor in order to capture also the fact that hydrogen is very sensible to the formation of clouds or to the movement due to the wind. The last test that I want to mention is the one with the mixture. which was, as I said, we already had some tests done onto the mockup, but we were not able to do any test with multiple gases and to see them in one shot. So we were very happy to use this new sensor because in just one release, we were able to detect nitrogen, oxygen, methane, and hydrogen. So you see the peak of methane here and the very small peak of hydrogen. But remember that we were releasing a mixture of 10% of hydrogen instead of the 100% of release of the previous releases. So we notice, in fact, the ability of the sensor to react. So in the end, just as a conclusion, I presented the CIST wind tunnel and the work carried out within the Hydra project involved the adaptation of the wind tunnel for this new testing. So before we made all our studies, the ethics studies, in order to be in a safe position for carrying out releases of flammable gases. And the Hydra test enabled the execution of these campaigns in different configurations and the preliminary assessment of the sensor response that will follow a field campaign. So this upgraded facility now is able to host more testing from any other who is listening now or that is interested in using an open flow wind tunnel. So thank you very much for your attention. Here you have a QR code leading you to the CIST Center website. And thanks again.
Thank you, Raffaella. And again, reminding everyone that if you have questions on the tunnel or on the activities in Hydra that Raffaella described, please drop them in the chat and we'll take them at the end of the webinar. So this concluded the first part of the webinar, which related to Hydra activities. And now we're leaving space to another project, a European project, which is called the CERT. We have here Professor Nelson Perozo from the Clausthal University of Technology in Germany, and he will present the activities and tests performed in the CERT project. So Nelson, the floor is yours.
Thank you. So, well, good morning to everyone. From my side, yes, Nelson Perozo, my name, as already mentioned. I'm working at the Technical University in Clausthal. This is in central Germany. And I have no slide talking about myself, but I can just say that I have a background in mechanical engineering and followed by a master's degree in petroleum engineering, specialized in natural gas supply, and also a PhD in petroleum engineering, also here at the University in Clausthal. I have been working as a lecturer for the last 12 years, focused mainly in the topics of oil and gas production and natural gas transport and distribution. And about hydrogen, yes, this is what I have been working the most in the last 7-8 years. And a big example is this project Desert. Yeah. Well, you can see now on the slide the outline of my presentation. I will show you a bit about the Desert project, followed by the experimental investigations carried out in the project, as well as the simulations. And the third part of the presentation will be about how do we measure H2 or hydrogen or other gases leakages from pipe connections. And finally, I will show you the safety measures we have implemented for carrying out our tests safely. Yeah. Well, we have the Desert project. Desert comes from advanced thread connected production string for hydrogen storage in underground formations. This is a project which has been granted with a number of 1011-57797, as you can see here. And the project started about 2 years ago and will be ending by 30th of June next year, and a budget approved of 2.5 million euros. So this is a project which has a consortium from 4 different countries. As you can see here, we have a company Tuasex and Tuasex Premium Connections, as well as a Technica Group. They are all in the Basque Country in Spain. And we have Enco Engineering Consulting from Italy, and C2T Research and the Johannes Kepler University in Linz. They are both located in Austria, and ourselves, we are in Germany. So we have, I can start by saying that, well, it is believed that the energy transition we have hydrogen is extremely important. It can be called as essential for the net zero approach. Yeah, and it is also thought that by the year 2050 we'll have an increase by a factor of 6 to 7 in not only the production of hydrogen, but also in the consumption. And this is also possible because talking mainly about green hydrogen, which is like the cornerstone of what we are all doing here. And it is the idea to have green hydrogen mostly produced. And we have that this is all possible also because growth of intermittent sources of energy production, such as the solar and wind power, which is kind of the fastest growing sector for electricity generation at the moment, globally speaking. And all this inertia coming from this hydrogen industry requires a large scale of storage capacities, which cannot be covered if we keep it doing it above ground. Yeah. So it is extremely important to think about underground hydrogen storage. Yeah. Why? Because of the high volumes. We have that. Compared to natural gas, only 1/3 of energy is contained in the same amount of volume of hydrogen compared to natural gas. Yeah. That's why either we need to have higher volumes or higher pressures. Yeah. And if we think about hydrogen storage, not only underground, but also above ground, we need to take into account possible leakages happening in the storage facilities and all the peripheries of these facilities. And also the chemical affinity of the hydrogen, because it's this gas get materials brittle. Yeah. Well, just to put you in context and what is for us relevant, without storing the gas, we cannot talk about the hydrogen industry. Yeah. And this gas has to be, as mentioned, mainly stored underground. And as you can see here in the left part of the slide is the all the components of the underground storage facility, beginning on the top with the wellhead, which is in charge of allowing the flow of the gas towards the surface facilities, and also to regulate this gas flow. Yeah. And from here going down, we have the well itself, which is composed of different tubing strings. The one here, which is kind of giving a coating to this well, is called casing. And this casing is cemented to the ground, so it cannot be removed afterwards. And the one which is for us relevant, not only for the desert project, also in our main tests here, is the tubing string, which is the pipe which is retrievable. And this is the one which will be in direct contact with the hydrogen. So we are focusing in the desert project on the design of this pipe string. And at the end of a well, you'll have the storage facility. Yeah, in this case, a reservoir. Yeah. And we have also, well, the wells come also formed by some certain safety valves, one located here, and some packers to avoid the gas coming in the annular volume between tubing and casing. Yeah. Well, the pipe itself, as you can see it here, is composed by a sequence of metallic tubes connected in line. Yeah. So we have these two pipes, which are called pins, have threaded connections at the end, and we have couplings, which are having inner threading. And by this way, we're screwing pin into the coupling, and the same for the side of the coupling until we have the whole pipe string. Yeah. And this pipe string is responsible for filling and emptying the cavity. You can see in the picture how this is a pipe which is connecting the reservoir on the storage facility with the surface. Yeah. And this coupling is mainly formed by a premium thread connection. Yeah. Which is having as feature a metal-to-metal seal, yeah, reducing the probability of gas leaks. So these are connections developed for deep wells, which are suffering high loads, high temperatures, and which are also used to produce and to inject, or well, in this case, to transport gases. Yeah. And they are capable to be assembled and disassembled without suffering damage in the threading. Yeah, this is something really important because it is not like the pipe, once it is installed in the well, it will stay there forever. Yeah, but in case there is a problem, you make to it is, or it will, or it might be needed to make some workover activities, and meaning that you will need to retrieve all the pipe string, and the way to do this is to unscrew each of these connections, yeah, and then to put the pipe back. And this might happen several times during the service life of a pipe, yeah, meaning that they should be able to be screwed and unscrewed several times. Yeah. Well, as main objective of a project desert, we have to the design and development and validation of this new pipe string. Yeah, so mainly focused on the threading, as you, which you can now see on the right hand side. Yeah, and important also here is to talk about the right selection of materials for these pipes. So in this case, we need to have CRI materials, so corrosion resistant alloys, not only because of the embrittlement action of hydrogen itself, but also because of corrosion agents found in the reservoir. Yeah? So we have the presence of chlorides, of sulfurs, and that's why the selection of material is really important here. And now we have the design of this threading, yeah, plus the lubricant solution selection. Yeah. And finally, this complete design will be validated by by a really strong test program, both in lab scale as well as in full scale, yeah, which I will be showing you in the coming slides. So you have here the overall approach of Project Desert, in which we began the project by defining the service conditions of underground storage facilities, which type of loads are found in these storage facilities, geometries, typical geometries, typical sizes, volumes. And this was complemented by defining also all the technical requirements for these pipe strings. You know, so we need to have a certain amount of volumes produced daily, and this will depend on the demand of place. But typically, diameters for pipes used for these applications are found between 7 inches and 9.958 of inches. So we're talking about pipes of 180 to 250 more or less millimeters of external diameter. Depending on also the load suffered by the pipe, how deep we're talking about, the depth of these wells, the pipes have to complement their geometry with a certain wall thickness, yeah, which yes needs to be able to resist all loads acting and during the service. And this all this, or after having defined all these parameters, we began with the pre-design of the threaded string connection and the pre-selection of steel grades, materials, and the coatings needed for these threading connections, and lubricants used. Yeah. And after having chosen this, I mean the pipe threading type and also materials coatings, we started with our testing program and simulation program as well. Yeah, we've did some modeling of the tightness based on BEM, and also some microstructural modeling, yeah, to determine the embrittlement process in each of the stainless steels which were contemplated during the project. And we started also with our lab scale testing, yeah, in which, as you can see the left side, some hydrogen permeability tests were performed, some fracture mechanic testing, triaxial load mechanic performance, tribological behavior, and lubricant stability tests. Yeah. Then, after having performed this test, final optimization of the threading based on FEA, finite element analysis, was performed. Also, the proper selection of the optimal material, coatings, and lubricants. Yeah. And once having all this finished, we are coming to the full-scale string test in the lab. Which is composed of two different test types. So we have the galling assessment of the thread connections, and we have the sealability test, yeah, in which we are measuring the hydrogen leakages. This is why I'm coming to this point for this presentation. Yeah. And after this, well, we have the final string design together with geometry and materials. And well, we finalize the project with the corresponding activities for exploitation, dissemination, and well, the rest of activities. Well, how do we measure leakages? I will come now with our full-scale testing. Yeah, and we have been testing pipes, full-scale pipes, for about 40 years in our laboratory. And as the norm requires, these tests have always taken place with nitrogen. And well, now we have updated and we have modernized our machine, one of the test frames, in order to be able to test with 100% hydrogen. And in this test facility, you can see here, we have a triaxial full-scale testing rig. And this is a machine which is able to apply combined loads on the pipe. And this frame is designed for testing pipes between 5.5 inches and 16 inches of diameter. So that means pipes up to almost 400 millimeters of diameter. The output, we have a determination of the mechanical integrity and the sealability of a thread connection. This is why we're performing these tests. So we have some other test facilities for testing the material itself, in which we just test pure tubes, steel tubes. But in this case, we are giving focus to the connection of a pipe string. And this is done by applying ad hoc full-scale galling and sealability tests, in this case for hydrogen, and under different triaxial load scenarios, which are the main idea is to replicate the loads which the pipes are subjected to during its service. Well, the first part of this test of full-scale pipes is the galling assessment. As you can see, the thread connection may suffer galling, and this in the picture is an extreme case of a galling case of a galling problem in the pipe. And how do we perform this galling assessment? Well, this is also something we do as the standard is stating. The idea is to make up and break out this connection several times, yeah, and up to a minimum amount of times. And there are different test samples chosen for these tests, and these test samples are having different geometries in the threading connection. So the threadings are cut with different geometries and with different interferences between the threaded connection of the pin and the coupling, yeah. And they have to be screwed and unscrewed. So as it is called in the oil and gas industry, to make up the connection and to break out the connection several times, yeah. And the connection has to stay without any damage. So this is the first part of the full-scale testing we perform, and this is followed by a sealability test. Yeah, this sealability assessment is performed having a really extensive test program. This, as the norm requires, the standard requires, we need to test up to 8 pipes with these different interferences in the connections, and the complete test program can take up to 6 months of time. Yeah. The idea is to subject the pipe sample and its connection to different load types. Yeah. What you can see at the left side is the load envelope of the connection. We have at the right side the application of axial loads and in tension. At the left side, we have compression forces also in axial direction. At the top here, we have the application of internal pressure in the pipe, and here the application of external pressures. So I'm showing you this, and this is how the envelope is showing you the different combination of these loads acting, yeah, because this is what is actually reflecting the reality. It is not like we have only axial loads and then we will be having internal pressures in the pipe and then temperature is applied. So you have to take into account that all these loads are acting at the same time, yeah. And this is what is making these pipes to suffer a really strong load scenario, yeah, and that's why this is all performed in this way, yeah. So we have different tests in which we are also applying bending into the pipe. This is also part of the test program, as well as high temperature tests. Yeah. So how do we measure leakages in these full-scale tests? Well, the pipes, as you see here at the left side, the coupling of the pipes are having 2 leak holes here in which we connect some leak rings, and those here are we connect some hoses which are coming into our leak detection system, yeah, which you can see here in the middle. And the idea is to measure volume changes in the pipe. So as you might imagine, when we apply loads to the pipes, the internal volume of the sample is changing. Yeah? And this is what we are recording and with our leak detection system. Yeah? And apart from these volume changes, if there is during hold steps, if there is continuous changes in pressure and continuous changes in volume, this is how we can, or this is how we start to find leakages in the connection. Yeah. So leak detection system is formed by water-filled glass tubes. So these are the pipettes, which are having some graduation here for us in order to measure the amount of cubic centimeters changing per unit of time. We have also water reservoir, a camera, which is, I will have in the next slide. So this, what you can see now here is the same drawing here, but now this is in reality. This is one of our leak detectors. Well, this is actually not connected at the moment, and it is going through a maintenance. That's why it's just having all this here. And but well, we have these pipettes, these graduated cylinders, which are the ones directly connected to the connection of a pipe, and these are connected to these water reservoirs. Yep. And we have this camera, which is measuring this water levels and the change of water level. And as the standard is requiring, this level changing has to stay below 0.9 cubic centimeters per in 15 minutes. Yeah. So what we do is we fill a protocol in which we measure the change in level, or the value of the level each 5 minutes. Yeah. And this is what you find here. If this value is changing with numbers above this leak rate, then we need to extend the whole step until the pressure is stabilizing, and this change of the leak rate is also stabilizing. Otherwise, and if this is not happening, we're having leakages in the connection. Well, now to talk about our safety measures. We're here in Clausthal performing not only full-scale testing, but also we have developed now also and as part of a project Desert, different one more test frame, in this case for small test samples. Yeah, and as well as these two test facilities and some other we have here at the Institute, we are more or less having the same safety measures, in which we can begin with showing you the gas detection systems we're using. We have detectors located in all the single spots where the leak might be possible. And apart from that, our technicians are also using portable gas detectors, yeah, just in the case they need to go into the rooms where the tests are taking place. Apart from that, each of the cabinets, for example, this one here, either bottle cabinets or where some leak detectors are found and any other equipments are found, are also having ventilation and air extraction, yeah, which as well as all high pressure lines are coming and having an exhaust to the atmosphere, so outside the building. And before all this was or as part of the design process of these ventilations and all these pressure lines, some flow simulations have also taken place, just to be able to rightly choose the sizes and the lanes where exactly do we need to set our extraction point into the atmosphere. Also, as part of these safety measures, it's important to mention that we need to always work with compatible materials. Yeah. Remember, we're talking about hydrogen activities, and which after some time we will have some degradation of these materials in form of embrittlement. And we have also, well, all equipment used is designed for hydrogen use. Yeah, so this is an example of a hydrogen compressor. This is an example of a ATEX2 pressure transducer. Also the designed for hydrogen and methane applications. Important also is to avoid high pressure and high temperature mixture of hydrogen with air. That's why we're flushing our lines with nitrogen before the actual application of hydrogen. And the volume has to be reduced as much as possible. And finally, we have the design and of an autonomous control system, which is in charge not only of controlling the test of the automatic application of pressures and loads, but also to react in case of deviations and of the parameters during the test, and also in case of leakages. And we need to take into account always the local international standards and regulations for safety. And well, the creation of a safety concept is always important, as well as HACCP analysis, in which we are considered all the risks associated to the tests. Yeah, and of course the proactive actions we need to take in case of a problem. Yeah. Well, thank you for the time, and yeah, we can proceed to the next presentation.
Thank you, Nelson. Very interesting presentation. We are a bit late, so we'll leave immediately the floor to Dr. Ceres Woolley from the Utrecht University. She will present her research on basically source apportionment of hydrogen. Rafaela, if you have a question, we'll leave that for the end of the webinar.
Okay, thank you for the introduction. I think I can be a bit quicker than the 20 minutes. So, yeah, I'm Ceres. I'm a researcher at Utrecht University. I also don't have a background slide, but I did my bachelor's and master's in physics, and then my PhD was on methane emissions. And then for the last 2 years, I've been working on hydrogen. And that's as part of the Environmental Defence Fund project, which I will talk about in a second. But this work that I'm presenting here has been kind of a side project that I've been carrying out, and we luckily had a very great master's student who has carried out most of this work. And yeah, actually last week we published this. So yeah, so firstly, what I'm actually hired to do is emission quantification, but it's part of a large project with the US and Europe, and we have science and technology providers, and we also have industry partners such as Air Liquide, Air Products, Shell, and Total Energies. And basically the aim of this project was to quantify emission rates of hydrogen across the value chain, and we do that with the Aerodyne Research H2 monitor. And yeah, I can't present those results yet as they're not published, but almost all of them have now been submitted as of last week. So there will be, I think, 7 papers in total, and 4 or 5 of them have already been submitted. Yeah, so yeah, look out for those papers soon. But yeah, for now I will talk about isotopes, because yeah, my PhD was on methane isotopes, and we had an instrument in the lab that nobody had been using for a while, and I had a bit of spare time, so I basically got the instrument up and working, and yeah, that's what I'll talk about today. So just some background. I think I don't really need to go over this for this audience, but hydrogen is viewed as a sustainable energy carrier, but the EDF project at least was motivated by the fact that it is an indirect greenhouse gas. So we want to, if there are leaks, we want to reduce those to make sure that the climate impact of the hydrogen is as good as possible. Through its reaction with ozone, it leads to warming. I'm not sure how familiar people are here. So stable isotopic composition measurements can be used to partition sources. So different sources react differently with the amount of deuterium and hydrogen in the samples, and then we get this delta D or delta 2H signature, which can distinguish between different sources. So the figure on the left is from a paper by Gibson et al. And this paper is basically a big review of all of the literature. And you can see that the white geological hydrogen has like a big range, but then the gray hydrogen or the blue hydrogen, which I'm aware that, the international IEA said that we shouldn't call it green or blue anymore, but in it's just a bit easier for this presentation. So I'll refer to SMRs as blue or gray and electrolyzers as green hydrogen. And then, there's very limited literature here. So these are only a few measurements that this is based off of. But basically, Gibson say that you can distinguish between methane from an SMR versus hydrogen from an SMR versus hydrogen from electrolysis. And then it could be used as like a regulatorily source signature, so that we can decide whether something is actually green when they say it's green. So green hydrogen through electrolysis and blue is through steam methane reformation. And then in this study we focus mainly more on the mobility sector, but also production, because we're based in the Netherlands. There's a lot of hydrogen refueling stations, there's a few electrolyzers around. And as I just mentioned, the Gibson et al. Say it could be used as a regulatory tool, but there's really very few measurements because these measurements are very hard to make, but we're very lucky that we have one of the only instruments that we can do this with. So the method, we took air samples in infrastructure in the Netherlands, Belgium, France, and Germany in 1 liter glass flasks. So the flasks are under vacuum. We simply open the flask and then we let the gas in. So here's some different stations that we measured at. So we are at an SMR here. This is at a refueling station. You can see the bundles of hydrogen cylinders here. Another refueling station whilst a DHL van was refueling, and also in Germany whilst a bus was refueling. That's just a few examples. And as I mentioned, we have, I think at the moment, it's the only system that can measure background samples of hydrogen for the delta D signature. And that's really valuable because then we can measure downwind of the source. We don't need to have pure samples. We can just go outside the fence line. We find the plume. Normally we have the Aerodyne instrument with us, and then we collect the sample. And this was developed by Ree et al. In 2004. And we have, as I mentioned, we restarted the instrument in the last year. And since then we have an instrument stability of around 5.9 ppb and 2.6 per mil. So the method. Basically, when we have the sample, it's just ambient background air, and we have to get rid of everything that's not hydrogen. So firstly, we have the sample. It comes from a multi-port valve where we can measure 6 samples, and then it's all automatic. So we attach them in the morning, and then throughout the day it runs. It fills the sample volume, and then it goes to the cold head, which is this section, which is cryogenically separating the gases. So and then we go on to the next stage, which basically this is a bunch of steps that filter out everything except hydrogen. So then we have pre-concentration. So at the cold head, everything, it's at 40 K. So almost everything condenses except the hydrogen, the neon, and the helium, and some N2. And then we have a molecular sieve trap, which traps everything else. and then another cryofocus trap. And then basically we are left just with hydrogen, and then we inject that hydrogen into a Thermo Fisher IRMS to get the ratio of the DH. And then also we measured the delta D H2O of, so the deuterium content of hydrogen, water, sorry. And this is also a similar method. Basically, there's a pre-concentration step where we fill a vial with just 200 milliliters of water. And then after some steps, it's then also carried to a Thermo Fisher IRMS. So as I mentioned, we went to a lot of different sources, but because we are measuring, we're not measuring pure hydrogen, we're measuring downwind of the source. In our sample, we have atmospheric hydrogen plus the source hydrogen. So we need to get the source signature, we need to just get the value of the hydrogen addition on top of the background. And for that, we use the Keeling plot method. This is used a lot in the methane world. And so basically you just plot 1 over the mole fraction against the delta D, and then the y-intercepts gives you the source signature, which is like what was shown in the figure from Gibson et al. So here's some examples. So this is one SMR we visited, and we took a lot of different samples, we plot them, we have a nice R squared, and then we get the source signature. And we do the same for the electrolyzers, and then basically we have this big results figure, and there's a lot going on here, so I'll go through it one at a time. So firstly, there's a lot of literature, well, a decent amount of literature, respectively to how much literature there is on this, for combustion sources. So we visited car parks, which are enclosed underground car parks, and we have quite high enhancements of hydrogen there because of the cold start of the engines, the incomplete combustion. We were seeing up to 2 ppm above background in these car parks. And there are literature estimates already from Gibson et al. So in the gray, you can see Gibson et al.'s source signature with the error bars. And you can see that from the 4 car parks that we visited, all of them are nicely in line with the error bars, which is a nice sense check that, the instrument was off for a while, and now we got it running again, but it's still in line with what the literature suggests it should be. And then the same goes for SMRs. So again, the gray is from the Gibson et al. Paper, and then we visited 3 SMRs, and they all also are in range of the literature estimates. And then we have this one little outlier point where we were in an industrial area and we saw some peaks of hydrogen, but we don't exactly know where these peaks were from. It could be, petrochemical site, or it doesn't fit into any of these categories, at least from what we think. And then, so, the most interesting part now is that the electrolyzer, we expect it to fall in this orange range. So that's the orange range. That's the fractionation equilibrium for the water hydrogen at 700 degrees, which is the temperature that, at 2 to 100 degrees, which is the temperature at which electrolysis happens. And then, so also Gibson expects the values to fall in line with this. However, we visited 4 electrolyzers and we see this really huge spread in source signature. I'll walk you through these. So when we saw this signature of around -50, we were so surprised that we went back again to measure the hydrogen again, and we got exactly the same source signature within error estimates of one another. And then we have one point over here, which is from a laboratory electrolyzer, and our calibration range is maybe can't go as low as this. So this value might be a bit lower than it actually should be. It may fall in here, but we don't have the calibration cylinders to calibrate that properly. And but however, you can see this really large spread in the source signature, which was really, we weren't expecting. We thought everything else is agreeing with the literature, the electrolyzer should too. And then, we have some points here somewhere in the middle. And then I should also point out that this data point here is from a commercial electrolyzer. So they are operating 24 hours a day, 5 days a week. And this one here is a lab one. So yeah, then this begs the question, can we really distinguish between blue and green hydrogen if with delta D, because this point here falls exactly into the range that the SMR should be falling into. And then the same happens for the hydrogen refueling stations. So we visited a lot of those, and the ones in green, you can see that those are ones where we know that it comes from electrolysis, so green hydrogen. So again, these 2 points over here, if you didn't know and you wanted to use it as a regulatory tool, you would think, oh, they must be from an SMR. However, we know that they're from electrolyzers. So yeah, we were thinking, why could this be? And we thought it probably has something to do with the water in the electrolyzers. So then we took samples from this electrolyzer, the laboratory one, and this electrolyzer, the commercial one, at the either end of the scale. And then we found this. So we took samples. The first row just shows the delta D of the hydrogen gas. And then we took samples of the source water. So that's just tap water. So Dutch tap water is around -50 to 60, and then they use demi water. And then you can see the very surprising thing. So electrolyzer A is the red point. No, electrolyzer B is the red point, sorry. And electrolyzer A is the one that was, all the way over here. And you can see that the water is really, 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 really heavy. So plus 200 is, very heavy water. And then this basically confirms our suspicion that the water has something to do with the source signature of the hydrogen. So then we spoke to the operators of this electrolyzer, and they basically they reuse the water over and over again. They only, once it gets down to a certain level, they top it up a little bit, but essentially as the electrolysis happens 24/7 or 24/5, the hydrogen is getting used up, and then the deuterium is left over, and we get more and more deuterium in the water, and then eventually that then affects the source signature of the gas that is released. And so, it makes sense when you think about it, but it's nice that we have this confirmation of that. So, to conclude, we had a surprisingly wide variability of isotopic source signatures of hydrogen produced in electrolyzers, spanning from -850 per mil to -50 per mil. However, the delta D source signatures from SMRs and car parks agree nicely with previous literature estimates, but we find that hydrogen produced in electrolyzers overlaps in isotopic source signature with hydrogen from the SMR, and this is because of the process water in electrolyzers can become strongly enriched in deuterium during operation, which then affects the isotope signature of the green hydrogen. And then, so Gibson et al. Suggested that measurements of delta D can be used to distinguish blue from green, but our results do not support this. So delta D may not allow for the unambiguous identification of green hydrogen. That's it. Some thank you to the technicians that helped us get the instrument running again.
Thank you. It was a really interesting presentation. Actually, thank to all the speakers, because all of those presentations were really nice and the results were really interesting. Are there any questions? I can also unmute microphones. So if you want to ask something, just raise your hand. Okay, Raffaella, you can go ahead.
Yes, I just posted the question, but I maybe it's quicker if I just ask. It's a question for Nelson, because of course, due to the kind of testing that we were thinking at the beginning with our platform, we are very interested in this transformation of. I think it is a transformation of the well into an injection section for underground storing of hydrogen. So I was wondering if the pipe that you are studying and the connection, of course, are a substitution of the original tubing that we may find in wells. So keeping in place the cement and the casing and just replacing the internal tubing, or if it is a pretty new one. And normally there's a packer that closes the well. You also think if it is, this is the setup, are you thinking also of substituting the packer with a hydrogen ready one, doing the test on this for leakage through the packer?
Yes, thank you, Rafaela, for the question. Yeah, indeed, first idea and what we're at the moment focusing in is just to act on the tubing first, because this is the one actually having the direct contact with the hydrogen. Yes, it happens that the packer is also set to avoid the hydrogen moving to other places. And yes, packers have also been tested. There are already publications about how these polymers are also tested on their hydrogen action. They will have to be also changed. Compared to wells existing nowadays, yes, the idea is to change beginning with the steels, and what we're proposing in the project is to have this new threading design just to avoid losses of integrity in time. So at the beginning, for sure, everything will be able to work properly, but the problem is what will be happening in 5, 8, 10 years. This is one of the main questions. This is something no one can answer at the moment. And casings, they are not so critical because between tubing and casing, we have some, this is filled with liquids. It's not an empty volume. So this is filled with also some inhibitors, corrosion inhibitors for the casing. Why? Because the critical part of the casing is that they cannot be replaced. They cannot be retrieved. They are cemented in the well. Contrary to the tubing string. But in the future, actions will have to be taken. And for the complete for the whole completion, let's say, of the wellbore.
Many thank you. Yes, if I can just add one thing, the problem of how much time does it last? It's the same problem that we have with pipes, where we do have to insert a portion of hydrogen in methane or in natural gas, because we don't know. Is it a 10% fine? We don't know, because
Correct.
we don't know how much it will last as a pipe. So it's very interesting what you are doing. Thank you.
Thank you. So maybe I can take the chance also to ask a question to you.
Yeah,
Rafaela.
for sure.
Yeah, and in one of your slides, you're mentioning that you have the in the wind tunnel, some sections are not painted, some others are painted. How is this affecting your tests and results?
But it's not painted, meaning that the obstacles onto the mock-up were unpainted because the paint was somehow creating sparks. So the very, very small sparks that could inject the flame. So from the fluid dynamics, it doesn't really matter because it's a minor in case contribution, but it's a part of the assessment. Of course, we also did as a procedure, etc., for being able to operate the tunnel in safety. And from these studies, it came out that one of the most dangerous situations was the creation of sparks. So we unpainted and repainted the mock-up with this particular paint. In fact, we have to be very careful when putting the tunnel, putting the sensor. You may have noticed that we used a tape that was a copper tape. It has an adhesive, but it's copper because from the outside, so that it is conductive too. So the key point is not to create electrostatic sparks onto the platform. And if it is scratched as a surface, it has to be repainted to recover the continuity of the platform. So it's quite sensible to these, but in fact, you are releasing pure hydrogen. So in just a few centimeters, you are in the range. So that's why you have to be careful. But from a fluid dynamics point of view, it doesn't really create troubles.
Yeah, it's more in terms of keeping the safety, to avoid some detonation, not detonation, but some explosions. Yeah. Yeah. Thank you.
Any other questions? I don't see any raised hand.
Probably I can ask another question, in this case to Veronica. Veronica, you showed also one of your slides the housing of this ATEX. Yeah, and just I can imagine. Yeah, I mean, you showed it was open, so everything contained in the housing. Are these housings having some I guess you did the design or part of the design of this housing, the geometry and also the materials. Just to ask about the material itself, is specific or special material which you're using here for this housing?
Okay, thank you for the question. Yes, I show the presentation as you can see, and also the other people can see. Yes, is designed ATEX EXD box. So he's in aluminium and other materials, but is precisely designed and certified directly by the customer that sent to us and is designed for ATEX certification. So we also certified all the instrument that put inside the box with the box, but the box has just his ATEX certification.
Okay. Thank you.
And also, I can add this thing. It is certified for both zone 1 and also zone 0, but our certification is for ATEX zone 1 because we have this strictly condition at Politecnico di Torino in the wind tunnel, but for the second part of test, so in Greece, where we will be in a couple of weeks, we have the zone 2. That is less strictly, but we prefer to do all with the zone 1.
That's good.
Thank you.
Thank you.
Okay. Oh, sorry. I raised my hand.
So you can ask.
Yeah. Actually, I did have a question for Ceres. I just wanted, because you mentioned that the isotopic measures you also perform for methane. So in that case, so the method works. You don't have any problem with the source partitioning with methane.
Methane between SMRs or just generally?
Generally.
I think generally, yeah, it depends on the region. So depending on where the oil and gas comes from. So the source, for example, in the UK where I did my PhD, we have most of the oil and the gas from the North Sea. So we can distinguish between waste and gas quite well with the carbon ratio. However, in other countries that my group for my PhD went to, for example, in Bucharest, with the carbon ratio, they weren't able to distinguish between waste and gas. And for that, they had to use the deuterium ratio of the hydrogen instead. So it's a bit, area dependent, but generally, yeah, it can be done quite well. And now there's a lot more measurements also even of clumped isotopes where they're measuring 2 of the isotopes. For example, 1 deuterium and 1 13C, sorry. And then that can distinguish, well, theoretically can distinguish even better, but that's even harder to measure. Yeah, but generally there's a lot more measurements on methane than there are of hydrogen. So there's a lot more gaps in the literature for the hydrogen isotope signatures than there are for methane.
We're also very looking forward to your research on the emission factors.
Yeah, so once it's published, then I can come back and present that.
Yeah.
It's been submitted, so hopefully within the next few months it will be out there.
Okay, so we are 5 minutes later than expected. I think we can close the webinar now, but you have the contacts of all the speakers, so you're welcome to ask questions directly and get in contact with them. Thank you all attendees and again to all the speakers for your very nice presentations.
Thank you.
Thank you.
Thank
you
you
very much.
Bye. All.
Bye.
Bye.
Have a good day. Bye-bye.
Bye.